Welcome back, and let us resume our discussion on offset of the comparator and the circuit techniques for mitigating the offset. Yesterday we started with the discussion on the offset in a differential amplifier and discussed the origin of offset and how to model it. We discussed the concept of input referred offset. In our case, we are looking at differential input and single ended output comparator. So, we have a output which is single ended, and we have the positive and the negative terminals. We discussed the sources of mismatch in the transistors, how process variation can lead to mismatch in the transistor pairs, load pairs as well as input pairs, and how we can figure out the overall effect of that mismatch. Now, here if we look at the overall scheme and try to see what can be the process through which we can mitigate the effect of offset in the comparator and hence on the overall ADC transfer characteristic. If you remember, yesterday we discussed how the offset of the two comparators that we are using, the NMOS input device and the PMOS input device, is going to impact the overall ADC transfer characteristics. And we noticed that if the resolution requirement of the ADC is even higher, maybe rather than 7 bit you are going for 8 bit or 9 bit higher number of bits, the resolution dictates or mandates that the offset must be addressed. If you have few tens of millivolts of offset coming over here, it would corrupt a lot of LSBs, or in other words, the corruption in the data or error in the data will correspond to a large number of LSBs. So, we would like to mitigate this offset using appropriate circuit techniques and look at the overall details of the circuit implementation. So, first we can look at the block level concept that is going to be useful for mitigating offset, and then we will go deeper into the circuit level implementation, the associated issues, and try to see whether the overall requirement for the offset cancellation scheme is being met within our circuit constraints. So, as we have done earlier, we can start with say assigning an offset voltage over here. So, suppose we extract the offset voltage from the comparator, whatever is the effect of mismatch in the input pairs, load devices, we extract it in the form of an effective offset voltage applied at the gate of the MOSFET. And then we are left with the ideal amplifier. Then we have completely matched NMOS pair and fully matched PMOS pairs. And then based on this, we need to look at the overall circuit scheme which can help us mitigating this offset. So, let us now look at the block level implementation of the offset cancellation scheme, where I have the non-inverting terminal. I have applied an offset voltage V offset, keep the polarity as such. So, the definition of V offset is the direction I have taken is plus minus in this direction, and I have the other terminal, the negative terminal as it is. So, this is the ideal amplifier constituted of the transistors of the diff amp that we have over here. It is having a single ended output. Now, the main concept involved in the offset is to first of all extract the effective offset voltage of the amplifier. So, if we for example close this loop and construct a unity gain feedback amplifier, what is the voltage we expect over here if I set this to say ground or an AC ground basically. So, suppose I set it to an AC ground, in that case we have 0 over here and this point is 0 plus V offset, and of course, if this is having sufficiently high gain, the amplifier will make sure that this point is also coming as 0 plus V offset. Therefore, the output point is V offset, output is having the signal V offset. And of course, the definition, another definition of offset voltage is the required voltage at the input, which is going to make sure that the offset, the output turns to 0, or the mid value. For example, if I apply a minus V offset input over here, then the minus V offset plus V offset will be coming 0, and then the effective potential over here will be 0, and then I can expect that the output will also be 0, equal to the input. So, that is another definition, the amount of input that you need to apply, so that the output level is equal to 0 in this case. Of course, 0 here means AC 0, it is an AC ground. So, in effect you can have a DC voltage or a DC bias point over here, something like a common mode voltage level. How does what is the basic mechanism which lets the amplifier follow the applied signal, or in this case say V offset. So, suppose V offset is an applied signal. So, you have the AC ground, on the top of that you have an applied V offset signal. So, what is the basic mechanism involved in the loop which allows the amplifier to follow? So, of course, we have a negative feedback loop, and if you look at the operation at the transistor level and construct the negative feedback loop, we can see what is the role of the two stages and each of the transistors in these stages in order to determine the closed loop operation. So, we are going to have a negative feedback loop. Remember, this terminal is going to be my positive terminal, negative terminal, because from here to here you have an inverting gain, and again from here to here inverting gain. So, if you increase this potential, this goes down, finally this goes up. Therefore, this is the non-inverting terminal. And suppose you have some DC bias point, both of them are having a certain DC bias point, and I am trying to connect, I am trying to establish a negative feedback. So, the output has to be connected to the inverting terminal, and then I am having suppose a DC voltage which is sufficient to keep all the transistors in saturation. So, of course, this DC potential should be such that the input devices as well as the bottom transistor is in saturation. So, I have some VDC, and on the top of that I am applying some signal at some instance, I am applying say a step signal, and let me call these, let me number these transistors 1, 2, 3, 4, 5 and 6. So, this is a step signal that I am applying at t equal to 0. So, before that this potential was at 0 plus VDC, whatever VDC you have applied, it may be VDD by 2, and let us assume that the output potential was also same VDD by 2 at that instance, and under that condition if I use the diode connected configuration, under that condition when the two input DC points are same, we know that for the differential pair both these DC points are going to be same, because if these two gate voltages are same equal to the applied DC potential VDC, I have the same current almost flowing through both the transistors, and upper transistors also have the same gate voltage, therefore, their VSG will be same, and hence the other variable which is VSD also must be same. So, we know that under common mode operation, if these two potentials are same, this potential is going to be same. Now, if you apply a step potential at t equal to 0 and this becomes VDC plus delta, what is going to be the response of these stages? We of course know that if it is a high gain amplifier, finally the output should settle to VDC plus delta. So, that both these potentials are very close together, that is the expected behavior. But what is ensuing that behavior, what is making the amplifier start towards that operation and finally stop when the output voltage over here becomes equal to VDC plus delta. So, at least at this node, of course, we have some parasitic capacitances which is coming from the the common source stage as well as the parasitic capacitances contributed by the transistors in this stage. So, I have some effective Cp over here, and when we apply a delta voltage over here at t equal to 0, we are creating an effective difference between the gate potentials of M2 and M1. We are increasing the gate potential of M2 with respect to M1. Therefore, of course, we know the differential amplifier operation will increase the current in say M2 by delta I, and since the total current is constant provided by this M5, there will be a reduction in the current going in M1. So, here you will have minus delta I, same amount. So, that plus minus the total current remains same. So, if I am increasing at t equal to 0, when I am increasing the gate potential of M2 by delta, I expect that instantaneously there should be a increase in the current in M2. Initially t equal to 0, both of them were same, but after t equal to 0 plus, this should be having delta I plus and this is minus delta I. And if I talk about the small signal operation, this is ultimately that you are going to have a reduction in the current in this direction. Whatever current was flowing from drain to source in this MOSFET, that is reducing. So, the change or the small signal can be represented as minus delta I flowing in this direction, and therefore, you have the same minus delta I flowing in the PMOS, and since this is forming a current mirror. So, if this is having minus delta I, we are ultimately having minus delta I in this direction also, in this PMOS also, because M4 forms a mirror with M3. So, if this is minus delta I, the M4 should also have ultimately minus delta I, mirroring the minus delta I in M3. And as a result, if I apply KCL at this node, what is the total current that I can expect coming out of this node? Here you have plus delta I in the downward direction, here you have minus delta I in the again downward direction from VDD to this node, or in other words I can say delta I from this node to VDD, right. As a result, I have effectively minus 2 delta I going in this direction, or in other words I can say if I represent this as minus 2 delta I current going into the CP, or in other words I can say that there is a 2 delta I coming from the CP into the circuit node. And if you have 2 delta I current flowing from the capacitor into the circuit, that means of course that the charge stored on the capacitor is reducing, and therefore, the voltage on the capacitor is reducing, right. That is the basic mechanism of the differential amplifier. Whenever you apply a delta V over here, you are creating a difference in the currents. If I assume this is plus delta I minus delta I, the delta I in the M3 gets mirrored into the delta I of M4, and then at this node if you apply the KCL, you are having overall small signal current minus 2 delta I flowing outside. And if I assume that you have the small signal resistances also, of course, they will be also contributing to some of that current. So, here I am not talking about the RO of the PMOS and the NMOS. In the usual analysis, you also have the small signal current paths, the ROs of the NMOS and PMOS. So, they will also be contributing to the KCL equation, but if I just look at the capacitor and see what is its behavior, so ultimately when it is supposed, this node is supposed to charge, this parasitic capacitance is going to increase or decrease depending upon the direction of the current flow, on the net current flow. And therefore, here at least if I look at these current directions, whenever the voltage over here is going up and this total current is positive in this direction, that is 2 delta I, that means the charge stored on the capacitor is getting dissipated and you are having the voltage over here reducing. And if the voltage over here reduces, that means the gate voltage of this M6 is reducing, VG6 is going down, and that means the current in M6 is going to go up, and that means that this particular potential, once again you are having another I can call this CP1, let me call this CP2, you are also having some parasitic capacitances over here. If this overall current is going up, once again you will have this node voltage going up, and as a result additional charge getting dumped on CP2 and it will try to increase this voltage. And as this voltage increases and finally approaches VDC plus delta, so this voltage also is going to shift from VDC to VDC plus delta. And as gradually this voltage approaches VDC plus delta, what is going to happen? Once again both of these become almost similar. As a result, the delta I plus minus diminishes, approaches 0, and hence the charging of the capacitor stops. There is, because under that condition whatever the small signal current delta I plus minus will flowing, they stop, because these two are now matched, and beyond that point you do not have any difference in the small signal currents at this node. You do not get an overall small signal current going into the CP. Therefore, this stops, and finally since this voltage stops rising, this voltage also stops rising and it settles to the value which is VDC plus delta. So, this is the basic mechanism which is present in the negative feedback loop, which is helping us in making the gate voltage of M1 closely follow the gate voltage of M2. So, we are going to use this same mechanism for extracting the information for the offset voltage that we have in the amplifier. So, let us see how we can do that. Any question in this operation, how the gate voltage of M1 is following the gate voltage of M2? Whenever you change the gate voltage of M2 by a small amount, how it is able to follow. So, circuit, the transistor level operation point of view also should be clear. So, of course, from the block level we know that amplifier with sufficiently large gain, it will also always make sure that these two potentials are going to be almost close or very similar, but at transistor level this is the overall operation involved. Now, how can we use this to extract the information regarding the offset? So, as I said, here if you have an amplifier with an offset rather than having a perfectly matched pair, you are having an offset, and then rather than putting a DC voltage over rather than putting an absolute 0, I can suppose I have a DC bias point which is say VDD by 2. So, I put a VDD by 2 over here, and as a result this becomes VDD by 2 plus V offset, and once again the amplifier should make sure that this point also is VDD by 2 plus V offset, and hence this is also VDD by 2 plus V offset. I am just taking VDD by 2 as a comfortable number because there is midway between the VDD and ground. So, if I have some DC bias point on the top of that, there is an offset present, and in the closed loop operation or in the unity gain configuration, the amplifier gain will make sure that this output also settles to VDD by 2 plus V offset. So, I am interested in extracting this quantity, and to do that the circuitry that can be used it involves a capacitor across which we would like to sample the offset voltage. So, we have say the negative feedback in action, and at this point we apply VDD by 2, a common mode voltage basically, and then we also apply the same potential over here. So, V out, which is equal to VDD by 2 plus V offset, is going to appear over here. Right. So, if the amplifier is connected in this fashion, where you are applying a VDD by 2 at the positive terminal, remember, to the circuit designer this is the terminal available, this is internal to the amplifier, we have just extracted it and modeled it as a source, but ultimately it is coming from the properties of the amplifier, mismatch in the transistor. So, this is not accessible to the user. To the designer, this is the point which is accessible. So, I can apply a desired voltage over here, DC, AC, whatever you want. So, this is part of the amplifier, we are just modeling it as a convenient delta V in series with the input device. So, now I have the VOS plus VDD by 2 coming over here at this point, and therefore, what is the effective voltage across this capacitor? VDD and VDD by 2 plus V offset. So, we have V offset stored across the capacitor in this direction. So, through this loop, through this configuration, closed loop configuration, I can extract the offset voltage of the amplifier and store it across the capacitor. I can call it say C offset. Now, the next thing is we have extracted the V offset, we also would like to apply it to the signal in such a fashion, so that the effect of this extracted voltage cancels or nulls the effect of the offset of the amplifier. So, in this loop itself, if I immediately open this after shorting the output of the amplifier to this terminal of the capacitor, if I open this and I also remove the connection from VDD by 2, So, suppose through some switch I had connected this point to VDD by 2. Now, also through some switch I had connected the output of the amplifier to the inverting terminal, and through another switch I had connected the inverting terminal of the amplifier to this capacitor. So, suppose in this operation that I just described, these three switches were closed, and therefore, this was having a negative feedback unity gain operation, negative terminal connected to the this terminal of the C off, and also this point was connected to VDD by 2. After that, if I immediately open these two switches and also this switch, what is going to happen to the capacitor over here, and what is going to happen to the charge that was stored at this node. So, if I assume that these two switches are opened simultaneously, after that this node becomes a floating node, because it does not have any current path through any other transistor. This is the input device, MOSFET gate. Ideally, it is having very large impedance. There may be some gate leakage current, small amount of gate leakage current, we can assume that it is very small, and this is the capacitor. So, whatever charge was stored over here at this node or on the negative plate of this capacitor, it has no other path to go, it will remain trapped on that plate of the capacitor. And therefore, whenever you have some negative charge on this plate of the capacitor stored, it will keep the positive charge on the other plate also intact, because it has electric field and you are having that negative charge over here which is not able to escape. So, it will also keep pulling that positive charge, and it will, that positive charge will also keep stuck at that point. So, because this becomes a floating node, after I disconnect these two and the negative charge stored over here is not having any path to leave, it will be stuck at this point, and the electric field, if I just zoom out this, you are having the suppose negative charge is stored over here, positive charge over here. So, that the delta, the total charge magnitude is going to be Q equal to C V. So, C offset times the V offset. This is the V offset, yes. So, you have this is the total charge which is stored on the positive and the negative plate of the capacitor, and the moment you disconnect this from VDD by 2, the charge at this node is remaining clamped, it has no other way to go, and therefore, it is also going to make sure that the positive charge over here also remains clamped. What does that mean? That means that the charge stored on the plate of this capacitor is going to remain fixed, and if the charge remains fixed, that also implies that the voltage drop across the capacitor also remains fixed, it is not going to change. So, just because this node is becoming a floating node and you do not have any path for this charge to go, you are able to trap the negative charges over here, and hence the positive charge on the other plate of the capacitor, and hence you are basically storing the offset voltage across this capacitor. And once you have this offset voltage stored, I can go ahead, I have opened these two switches also. So, now it has become an open loop amplifier, and then I can basically apply my inputs to the two terminals of the comparator through another switch. So, if I had these three switches operating in or getting on in phi 1 mode, if I call this say phi 1, which is one clock phase, this is phi 1. So, these three switches were opened or were closed in phi 1. So, when the phi 1 phase came of the clock, this is phi 1 phase, these three switches were closed, and as a result you had the negative feedback implemented over here, negative terminal shorted to the positive plate of the capacitor over here, and also this terminal connected to VDD by 2. But now, I am opening the phi 1 switches and then connecting the phi 2 switches, phi 2 to the two inputs that I want to compare. So, here now I can have my two inputs, say V in minus and V in plus, which can be the circuits that we the signal that we have, the ramp signal and the input sample signal, suppose any two signal, any two analog signals. So, in the phi 2 phase, I close the two switches over here, other switches are getting opened, and therefore, what is the equivalent circuit that I will have in the phi 2 phase? So, this can be given as phi 2 phase. So, when phi 1 is off, phi 2 is getting on immediately. If I assume that, then what is the equivalent circuit, resulting circuit? If I keep this as it is, and try to draw the corresponding circuit in the phi 2 phase. So, you have the inputs getting applied to the negative and positive terminal of the amplifier, but in the positive terminal I have this C offset coming in, which has V offset voltage stored across this. This is V offset voltage stored across this, and then you have the actual offset voltage of the amplifier with polarity given by plus minus V offset over here, and then you have the positive terminal, negative terminal is directly connected to say V in minus, and you have V in plus, and this is the output. So, this is our normal comparator. Only thing is we have the offset voltage stored across the C offset coming in series with the offset voltage, original offset voltage that was modeled at the positive terminal of the amplifier, and as a result these two coming in opposite polarity in series, they get cancelled. As a result, the effective potential over here is just V in plus, and here you have V in minus, the internal terminals. Therefore, what I can say is that the stored offset or the stored voltage across this capacitor has been able to cancel out or mitigate the effect of mismatch. So, whatever offset was present in the amplifier, it captured it across its terminals, and that came in series with the applied signal, or sorry, in series with the amplifier's offset, and therefore, it nullified the effect, and then I have close to an ideal amplifier with 0 offset. So, if I look at how the signal is seeing the comparator, it is having two terminals over here, and the C offset is storing the V offset with opposite polarity, and it is getting cancelled with the V offset. So, this is the overall functionality or the overall principle for the offset cancellation. There are also terms that auto zeroing, which can be used for cancelling offsets in comparators as well as amplifiers. Even the front end amplifiers may be having offsets, and in certain cases cancellation of those offsets can also become important. Right now, so far we have not discussed the issues related to offset of the front end amplifier. We will see there the concerns are significantly different, and we will see what techniques can be used over there to mitigate the offsets, and whether it is equally important concern over there. Here we have discussed with respect to comparator what is the effect of offset, what is the effect on overall comparator performance, and also the ADC characteristics. So, ultimately we have the overall offset cancellation circuit given by this scheme, where we can call it say any particular VDC, it can be VCM, and then you have switches over here connecting the negative feedback, and then also you have switches over here. So, these three switches operate or get on in the phi 1 phase, and then you have the other switches, other two switches which are getting on in phi 2 phase. So, this is the overall scheme that can help us in cancelling the offset in the amplifier using the auto zeroing scheme.
So, do we have to consider the compensation for the capacitor?
Yeah, we will look into that. Of course, when we are going for closed loop operation, we have to be concerned about the stability during that operation. So, we will look into that. Gradually, we will try to build upon all the non-abilities in this circuit and try to see whether we are meeting the constraint, at least for whatever specs we have chosen for this amplifier, whether with the same specs we are able to comfortably meet our closed loop operation.
So we have to use something clock for stability. One thing may not be possible. So what should be the specs of that? How periodically we charge it?
That is a good question, and we will look into that. So that of course relates to the size of the capacitor. If the capacitor size is large, you can keep the stored charge over here for a long time without getting it destroyed by leakage. In that case, you can refresh it very less often. For example, for the entire conversion cycle, you can do it just once. Before the ramping starts, you can do it once. If the capacitor size chosen is small, then you will need to refresh it frequently. So, of course, there is a trade off. If you want to save area and make this capacitor small, you will have to go for very frequent updates.
We have to model the offset voltage only at the positive terminal.
We can model at both the terminals. So, we can also divide it V offset by 2 plus minus over here, but this is convenient for explanation.
If the offset is present at the negative terminal, then how do you apply the feedback?
The same thing. So, whether the offset is present here, you have a plus minus and you have a V offset over here. So, it is equivalent to applying a minus plus V offset over here. So, hardly the same thing. Okay, let us take a short break and then resume our discussion on the details of the circuit design.